Alright, so today, this is going to be our second mini lesson. Our first mini lesson was on energy flow. We talked about that, okay, we talked about 10% law, 10% rule. We talked about energy pyramids, we talked about that kind of stuff. Today what we're going to do is we're going to talk about nutrient cycling. So again, the difference in the terms flow versus cycling, I brought it up last time. But in this case, the idea of, the visual I use personally is the concept of take a bucket. Okay, if I have a bucket and I put it underneath the sink over there and I turn the sink on, the bucket's going to fill up and eventually it's going to get to the top. And as more water comes in, the rest of the water is going to flow over the side, right? I think of energy that way. You have a constant input of energy, okay? It flows through the system and then it is lost eventually, and you have a constant input and a constant loss of energy in the system. The way I look at nutrient cycling is if you want the concept of water again, think about a fish tank. In the case of a fish tank, it stays self-contained. So what happens is the water that's in the tank gets pulled up into the filter, it gets filtered, and it gets dropped back into the fish tank, right? And it constantly flows up, through, back in. Up, through, back in. As opposed to having any sort of constant input of water, in this case, you're just cycling the water. Well, that's how nutrients are in an ecosystem. Nutrients are cycled. There's a certain amount, and it's just constantly cycled, as opposed to energy, which is a constant input of energy and eventually loss of energy over time. So again, just a visual to help with those two concepts, okay? All right. Now, what we have to really get to first is the concept of what we mean by nutrient. Because I think we have a sense of nutrients is different than what we mean in terms of biology. When we're talking about biology, we're talking about nutrients. We're talking about certain elements. Specifically, in life, there are 6 primary elements that make up 96% of all material found in living things. And it's these 6 right here. Carbon, so let me write these down here. Carbon, remember, all these things are posted online. All these slides are posted. Actually, they're there already if you really want to pull them up as we did it. Okay? Hydrogen, oxygen, nitrogen. Anybody know what the P is? Phosphorus. Good. Phosphorus. For us, maybe. I don't know. Don't grade me on spelling. And what's the S? Sulfur. It's sulfur. Okay. These 6 elements. So you think about the periodic table. There's like 120 something elements on the periodic table. These 6 right here make up 96% of the atoms, the elements in living things. All the rest of them are just like made up for other things, We have a few other ones in there. Calcium, obviously, is found in our body and things like that. We've got some other major ones that you'll find along the way. But these 6 make up 96% of all living things, okay? Now, what do we use these for? We use them to make up organic compounds. Now, later in the year, we're going to spend an entire kind of unit talking about organic compounds. So you'll actually talk about the structure of organic compounds, what these things look like. But you need at least a brief introduction to them to understand why these things are so important. Okay? These 4 organic compounds, carbohydrates, lipids, proteins, and nucleic acids, okay, those are what we consider to be organic compounds. They're in your body. Carbohydrates, also known as sugars. We talked about those in nutrient cycling, right? In energy flow. So why do you think that carbohydrates are so important? What is the function of carbohydrates? Energy, right? They're energy. Anybody know what lipids are for? They are fats. But what do fats do? They can, long-term storage is one thing. Long-term storage of energy, that's one thing they can definitely do. What else? Insulation, not heat themselves, but insulation. Okay, structure. Think about your cell membranes. You guys learned about cell membranes before, phospholipids. Okay, those are fats. Those are lipids. So we're talking about insulation, structure of like cell membranes, long-term storage. Long-term storage. just getting the basics here. Proteins. Proteins are hard. I don't know that I can say to you and do a generic blanket statement to say proteins do this. Because proteins do everything. They really do. I mean, they are the most versatile organic compound. Okay, proteins make up about 50% of the dry weight of your body. Okay, they make up 50% of the dry weight, and they're involved in so many different things. They're catalysts. You know what a catalyst is? You can tell me what a catalyst is. Anybody can tell me what a catalyst is? All the way back there?
Yes, a catalyst is a protein that assists in chemical reaction because it lowers the activation energy needed for the chemical reaction.
Very true. It speeds up chemical reactions. Okay? Speeds up chemical reactions. The one thing he said that isn't actually true, all catalysts, let's see, all catalysts are not necessarily proteins. Okay? You can have an inorganic catalyst, but in this case, when we talk about proteins, obviously we're talking about organic ones. We call them enzymes. You may have heard that term before. Okay? I remember back in the day when, I wear contacts. I've worn contacts since I was, whatever, your age. Okay? Actually before. And I used to have to use an enzymatic cleaner. Now I just throw them away every day. Okay? But I used to have to clean them. And I had to put a tablet in there, and it was an enzymatic cleaner. And basically what it did is it broke down the protein stuff that developed on the lens over the course of the day and would clean them off. It basically fizzed. It almost looked like, what do you call that? Not Pepto, but what's that thing you drop? Alka-Seltzer. You drop it in and it fizzes. That's what the enzymatic cleaner was like. I dropped it into the liquid. I added the liquid to it, and then it fizzed, and it was supposed to grab onto the stuff on my lenses, and I use them forever. I use them for an entire year, the same lenses. Now, daily, I throw them away. There you go. All right, so we can use them for catalysts. They speed up chemical reactions. They're involved in transport. For example, hemoglobin. Hemoglobin is a protein. It transports oxygen around your body, right? So it's involved in transport. Structure. Proteins are involved in structure. They make up some of the cell membrane. Just like the phospholipids, there are proteins embedded, okay, in the cell membrane. They act as structure, they act as channels, they do lots of different functions. Let's see, what else do proteins do? Catalyst, transport, structure. I mean, they're involved in immune response, they're involved in almost everything. So again, it's just, you have to understand right now anyway, that they are very versatile in terms of what they can do. And a lot of it has to do with the ability to bend and fold in a lot of different structure. And structure is related to, anybody want to finish that sentence? Structure is related to function. Okay? That is a generic term across the board, doesn't matter what you're talking about. The structure of something should be related to its function. A spoon is designed a certain way to do a certain job. Just like proteins can fold and bend a certain way to do a certain job. Okay? Alright, and then finally nucleic acids. Anybody tell me what a nucleic acid is? Or what's it for? You guys know it by their generic terms, by their generic names, and if you don't, I don't know what to say. So maybe when I say their generic names, you'll be like, oh, at least I hope so. Anybody know the generic term? DNA, good. Heredity. They're heredity. They're involved in heredity, and we're talking about DNA and RNA. Okay, good. Now, going back to the last slide, we're talking about carbon, hydrogen, oxygen, phosphorus, nitrogen, sulfur, those being the 6 primary elements. Carbohydrates contain carbon, hydrogen, and oxygen in a 1 to 2 to 1 ratio, and you see that when I talk about glucose, C6H12O6, for example. Okay? So in that case, that's an example, that's glucose. Actually, it happens to be a number of different ones. It's galactose also, but who cares? Okay? But glucose, C6H12O6, 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. Lipids also contain carbon, hydrogen, and oxygen, not in that 1 to 2 to 1 ratio. They have a much higher carbon and hydrogen ratio than they do oxygen. Don't worry about that right now. Proteins. Proteins also contain carbon, hydrogen, and oxygen, but they also contain nitrogen and sulfur. Okay, carbon, hydrogen, oxygen, nitrogen, and sulfur in proteins. And then nucleic acids contain carbon, hydrogen, oxygen, nitrogen, and phosphorus. Okay, they do not contain sulfur. The reason I'm telling you this is because when we start talking about the cycles, you need to understand why it's so important that we cycle nutrients, one. And two, you also have to understand where they're going once they enter a living organism. What do they become part of? Why do I need nitrogen? I need nitrogen for proteins. Proteins make up 50% of the dry weight of my body. So therefore, they're very important. Okay? Why do I need phosphorus? Again, they're part of my nucleic acids, my DNA, my RNA. I need those. Sulfur, what do I need sulfur for? And so on and so forth. Okay? Alright. So, let's go to the next slide here. So the first one here is the carbon-oxygen cycle. In here, as far as biology is concerned, our focus is going to be on what we call the fast carbon-oxygen cycle. And when I say fast carbon-oxygen cycle, it consists of basically two things. Cellular respiration and photosynthesis. Those are the primary components of what I would consider to be the fast carbon-oxygen cycle. Now, when you say, well, if there's a fast carbon-oxygen cycle, is there a slow one? The answer is yes, there is. And a lot of that has to pertain with this down here. Okay? You're talking about your fossil fuels. The formation of fossil fuels, the storage of carbon. If you look at the numbers up here, you can see here it says 120 in yellow, and then it says +3 in red, and then it says photosynthesis. And then over here it says 60 in yellow, and then it says plant respiration. And over here it says 9 in red, human emissions and things like that. Okay? You can see numbers down here, 2,300, soil carbon, fossil carbon, 10,000. If you read the little description at the bottom, it says, this diagram of the fast carbon cycle shows the movement of carbon between land, atmosphere, and ocean. Yellow numbers are natural fluxes, and the red are human contributions in gigatons of carbon per year. So the yellow ones are natural, they're natural to natural cycle. So you look at those, you're talking about these right here, 120, 60, 60, okay? So you can see those numbers here, 90, 90, okay, that kind of stuff. So you can see that those numbers basically balance out. 120 coming in, okay, all right, 60 going out when you're looking at just the yellow ones. But you throw in the red ones, which is humans, add to that, that throws the balance off a little bit, doesn't it? Those numbers aren't equal coming in and going out. White numbers indicate stored carbon. So down here, these are carbon, what we call reservoirs. They're areas where we store carbons for longer periods of time or stay relatively constant over long periods of time. They're not part of that cycle, that natural flux on a yearly basis. Obviously, some of it will be released. Depending if we burn the fossil fuels, it'll be released. If we make fossil fuels, they'll be contained for long periods of time. Okay. All right. So that's the carbon-oxygen cycle. Now here, I've got a little video to show you here. It's funny because when I first watched this video, I was about to stop it about like 20 seconds in, okay? It gets better, I promise, okay? It's a little cheesy. I'll stop it. We'll talk a little bit as it goes through. It's only a few minutes. It's 4 minutes. But I'll stop it. We'll talk about it, things like that. But bear with it. It starts out, the whole thing is a little bit cheesy, but it's got some good information in it, okay? So stick with it.
Carbon. It can be found anywhere on Earth and makes up an important part of all living matter, such as plants, animals, and humans. This is its king. As well as in living things, carbon is found in the atmosphere in the gas carbon dioxide and is dissolved in water such as...
So look, we're about 30 seconds in and you're like, oh my god, I'm ready to turn this thing off, okay? And I was the same way. When I stuck it out, it was worth it. That's why I put it in here, okay? So stick it out.
...as oceans and rivers. It's also found in rocks, shells, and in fossil fuels. All the movements between the different places where carbon is found make up the carbon cycle. Don't worry, I'll explain it to you. Let's start with the land.
Start to get a little better.
Plants and trees use carbon dioxide from the atmosphere through photosynthesis.
That's a given. You guys are familiar with that. You know that carbon comes into a plant, carbon dioxide, water, plus sunlight. Okay, that's the photosynthesis, that's the reactants in photosynthesis. Okay, you know that they come in. Now, the other part of this, and somebody brought this up to me the other day, they go, Mr. Corvo, plants also make carbon dioxide, don't they? And the answer is yes, they do. They do contain they do contain mitochondria and chloroplasts. They contain both. If you're a plant, do you need energy?
Yeah.
The answer is yes, okay? You need energy. Photosynthesis does not give you energy. Photosynthesis gives you sugar. It doesn't give you energy. It gives you sugar. And then the sugar, when it's broken down, that's what releases the energy. So understand that the first step in energy transformation is photosynthesis. But that does not get you energy. That gets you the potential for energy. Then when the sugars are broken down, that's where the energy is released to do work, to do metabolic functions and things like that. So plants do both cellular respiration and photosynthesis. It's just that they do a lot more photosynthesis than they do cellular respiration. But that is a very common misconception. Plants do photosynthesis, animals do cellular respiration. Okay? Plants do cell respiration and photosynthesis. They just happen to do more photosynthesis than cell respiration. And that's what they're going to say right here.
They store carbon as they grow, releasing both carbon dioxide and oxygen. Animals and humans also give out carbon dioxide when they breathe. Carbon can also be released if plants are burned, and when they decompose and become part of the soil.
Okay, so think about this. Going back to my slide here, think about what they just talked about. They talked about carbon coming in the form of carbon dioxide into plants, some of it being contained in the biomass of the plants. That's where this white number comes in, 550. Okay, in the biomass of the plants. Some of it is released as respiration, and you can see that microbial respiration and decomposition here, okay, coming out as 60%. Over here, same thing, 90% coming in. Understand, a lot of times we focus on the carbon-oxygen cycle in the form of terrestrial environment, but also, 75% of this planet is covered in ocean. There's a good portion of photosynthesis that actually occurs in the ocean as well. There are photosynthetic plants and organisms in the oceans as well. And you can see that balances out with exchange there. So that's what they were just talking about. And then some of it goes down into the soil carbon, and then some of it eventually ends up as fossil fuels.
When dead plant and animal matter accumulates faster than it is decomposed, some of it can be compacted and transformed into fossil fuels, such as gas, oil, and coal. It took millions of years to make these fuels naturally, but we are burning them much quicker than it took for them to form. Dead plants can also float down rivers, which is one way carbon is transported from the land to the ocean. So far, carbon is present in photosynthesis, respiration, decomposition, compaction, transformation, and transportation. Phew. Okay, now the water cycle. Carbon moves both ways between the ocean surface and the atmosphere. Ocean plants use the dissolved carbon dioxide in the water for photosynthesis.
So what happens in the case of aquatic environment is carbon dioxide actually dissolves in the water itself. And so does oxygen. Oxygen and carbon dioxide both are dissolved in the water. That carbon dioxide in the water is what is taken up by the plants and other photosynthetic organisms in the water. And then oxygen is created and released into the water, and it's dissolved there to be used as the animals and stuff. And that's actually what fish will use, is they'll take dissolved oxygen in the water. Oxygen levels are lower in water, but oxygen is there. You and I can't use it. Our lungs don't allow us to take the dissolved oxygen out of water, but gills and fish and things like that do allow for that.
And they store this carbon just like the land plants. Then, ocean animals eat these plants, and so the carbon gets transferred again. Ocean plants and animals release carbon dioxide back into the water through respiration. Some ocean animals use the carbon in the ocean to make their shells. When they die, their carbon-filled shells dissolve or settle on the ocean floor. When ocean plants and animals die, they decompose in the water. The decomposing plants and animals either sink and dissolve or settle on the ocean floor where they get buried in the sediment. Over a long period of time, rocks may form and wear down, which also contributes to the carbon cycle. Finally, water moving between the different layers of the ocean also carries carbon. So why is the carbon cycle relevant to humans? Well, we know that levels of carbon in the atmosphere have increased a lot in the last century. This is largely due to human activity, especially the burning of fossil fuels and deforestation.
One of the things that this unit is matter and energy transformation. That's what this unit is, Unit 2. Unit 3 is interdependence. And what we'll talk about more in Unit 3 is human impact. We'll talk a little bit more about, global climate change a little bit, and our contributions to some of that global climate change. So we'll talk a little bit more about that in Unit 3. I'll let this finish out. But just understand that will come back in Unit 3 a little bit in terms of interdependence of organisms and that balance.
When we cut down and burn trees, they can't soak up any more carbon, and they release the carbon they've stored during their lives. And when we burn fossil fuels, more carbon is released into the atmosphere. For example, to run cars, produce electricity, manufacture goods, and heat homes. There is a limit to how much oceans and land can soak up. So on the whole, carbon levels in the atmosphere are increasing. Since carbon is a major greenhouse gas, this contributes to climate change. Not just the rise in temperatures we are now seeing, but also the rise scientists predict will occur over the coming decades. We all use energy in our lives, which mostly comes from the burning of fossil fuels. By reducing our own carbon dioxide emissions, we can do our bit to help tackle climate change.
Okay. All right. So, again, the oxygen-carbon cycle here, I told you, for our purposes, especially in biology, is going to revolve around these two major events: photosynthesis, cell respiration. Okay. From a nutrient standpoint, okay, again, we talked about these two things already from an energy standpoint, but from a nutrient standpoint, carbon and oxygen cycle, you've got photosynthesis where you have carbon dioxide, which is a small carbon molecule, only has one carbon. Okay, you're taking these are inorganic, they're not organic, floating around in the air right around us right here, plus water. Okay, and again, I'm going to balance this. Plus that sunlight, which is my energy input, yields a large organic molecule plus oxygen. Last time I talked about this formula, we were focusing on the energy component of it. This time I want you to focus on the nutrient part of it, the carbon, the hydrogen, the oxygen. You'll see that the carbon on each side is balanced and all that kind of stuff. But more importantly, going from photosynthesis into cell respiration, the products of one reaction are the reactants of the other one. So C6H12O6 plus 6O2 yields 6 CO2 plus 6 water plus energy to do work. So the focus this time we're talking about these formulas is about the carbon and oxygen and not so much on the energy. Energy is still important, don't get me wrong. I mean, you can't ignore the energy, but it's more about the carbon and oxygen. And when you guys start thinking about your ecosphere, or if you've done your ecosphere, you know that there was a delicate balance between your carbon and oxygen in your respiration and photosynthesis within your ecosphere. At least there should have been. That would have been one of the things that you needed to be considerate of. You can't have too many animals doing too much respiration because you won't have enough sugars